So this week we'll talk about cryptography a bit and see how it's been used for what we use day to day. What are some of the tasks? All right. So why did I choose this topic? Like in April, after the initial ship it was discontinued, so I had like 2 weeks in hot pocket where like we I had to study about like how documents can be securely transferred and like personal information for because this kind of hot pocket IXRPL project works with secure information. So that was one reason I started looking back at this cryptography stuff, and then also because of this working from home, as the working from home things started around the whole world. So we had some Zoom news with like it wasn't doing end-to-end encryption as it like promised. So there was some news on that as well. And also once we rejoined the Shipit team, so the guys again sent us the like some credentials for like Amazon logins and all. And what they, so initially they requested us to, me and Ravindu, to create some key pairs so they could send us the encrypted information, not just sending them in like sharing them in a chat application or email. So initially, personally me, I was not very familiar with these key pairs, even though we have like studied about these things in uni, because now that we don't use them much, so I have forgotten about them. So I had some trouble initially to decrypt the information, but then after I'm searching, it was we were able to figure that out. So that's why I thought maybe we should like it's time to revisit cryptography a bit and see how these are used today for what we use day to day. All right, so how? So we will not be worrying about the mathematics because these, as you know, these encryption mechanisms, this cryptography uses like pretty complicated maths. So we don't want to look at that, but we'll kind of quickly go through a recap of what we have kind of learned in the uni, and to like remember some basic information, and then we'll see some of the tasks that we use every day. They are using cryptography to secure our communications. Okay, so we look at the difference between symmetric and asymmetric key encryption. I'm sure you have heard about these things. And then we'll look at how we do key exchange for symmetric key encryption. So there are a lot of ways, but we'll look at a simple way, something that is most used. And then I'll do a quick demo on like public key encryption using the key-based set. And we look at how SSL and TLS that we use every day when we connect securely to websites and web APIs uses cryptography, and also briefly look at end-to-end encryption as well. Okay, so symmetric versus asymmetric key encryption. So the main difference is, so in symmetric key encryption, there's a single key to both encrypt and decrypt the messages that are sent between two parties. And in asymmetric key encryption, we have two keys, one to encrypt the message and another to decrypt the message. In symmetric encryption, the ciphertext is what the output of applying the encryption function into our message. So this is either same or smaller than the message. So it won't be much bigger than the original message. It will add some, it might add some headers that are fixed length. But in asymmetric key encryption, the ciphertext can be larger than the actual message. So in reality, like in practice, it could be like a 10% increase. So if we consider like a 1 gigabyte of transfer, if we encrypt it with asymmetric key encryption, so it would add another maybe 100 MBs. So when we talk about these bandwidths and online communications, that is too much. So that is a considerable amount. And also, so this third point, the being asymmetric key encryption being fast and symmetric key encryption being fast and asymmetric key encryption being slow. So this deals with this is because of the mathematical formulas and big key sizes that are being used. So for symmetric keys, we usually have like 128 or 256 bit keys, but for asymmetric keys, they can even go up to 4096 bit keys. So because of that, the encryption process can be slow as well as computationally intensive. And we also have to bear in mind that key generation also has to take place for public key encryption. So the generating these much bigger keys are also computationally intensive and it takes time. All right. So the primary goal of the symmetric key encryption is to provide confidentiality. So bad guy who's watching the communication between two parties cannot understand what is being communicated just by looking at the message that is being passed. Compared to that, asymmetric key encryption, it provides confidentiality as well as authenticity and non-repudiation. So authenticity means if someone sends a message, the receiver can verify that this message has been sent actually by the person who say it, the person who actually says it sends it. And so the non-repudiation also goes in line with that. So non-repudiation is so if I say I sent let's say so Ravindu got a message from me and I have signed it using my secret keys. So in a later date, I cannot say that this is I didn't send that. So these are important characteristics provided by the asymmetric key encryption. And in real life, in real world applications, so symmetric key encryption is used to transfer large amounts of data because of the fastness as well as the payload that it has compared to the asymmetric key encryption. So asymmetric key encryption, we use it to transfer some small amounts of data. So usually they would be secret keys. So the main issue with asymmetric key encryption is to figure out how to exchange the key. Because we have to remember that the key has to be exchanged in a non-secure channel. So someone looking at the channel can easily, if we just pass the key in the non-secure channel, someone else can grab that as well. So in the past, like in Caesar's time and like olden age, so these are some methods that have been used to like communicate the secret key, exchange the secret key. So meet in person, or maybe send it via a trusting courier, or we can even use a predefined set of keys. But again, for this, at least one time you have to initially meet and do that agreement. So nowadays with these applications, we cannot use these techniques, and yes, so because the key has to be exchanged in a non-secure channel, we have to look another way. So this is where key exchange algorithms or processes come in. So Diffie-Hellman is a commonly used exchange process or algorithm. I think we have learned it at the university as well. So I just took this graph from Wikipedia. So this kind of illustrates what the process actually does without going into the mathematical details. So our goal is to build a key together while communicating through a non-secure channel. So let's say we have two people called Alice and Bob. So we start with the common parent, but each person generates a private secret as well. So this private secret is never exchanged through the non-secure communication channel. So what happens is, so after the process is done, both the persons will arrive at the same common secret thanks to how these mathematical formulas work, and so this then we can use this shared common secret key to do the actual message communication. So what's important here is this mixture separation. This is computationally intensive when it comes to the actual mathematical numbers that are used in the real world. So no one can brute force and figure out the common secret key or the secret colors of the two persons by using brute force attacks. So we don't need to really look at the maths, so just having a general idea is enough. All right, so that is about the symmetric key encryption. So now we'll kind of look at the public key encryption. So what happens is a person will have two keys, a public key and a private key. And if say if Bob wants to send Alice some information, he would grab the public key of Alice and encrypt it with that public key. So Alice has the private key. So because of this, how these mathematical formulas work, only that private key that Alice has can be used to decrypt the message or ciphertext that is encrypted with the public key. So let me. So keybase is something that me and Ravindra had to create accounts to generate some public keys. So let me. Okay, so I am logged in from one of my accounts, so my Shipit account here. So I will also log into my personal account from Chrome as well. Yeah, so I already logged in. So let's say Keybase is a service that provides that allows us to generate a key pair, and then we can use the UI. But in real life, we should not use the UI because we cannot trust. I mean, we cannot trust if this website is compromised as well. So we'll look at how to do it manually later. So for the demonstration, let me quickly once this key base key pair was generated for the account, so the server stores the public key, so we can someone else in the same ecosystem can find that person. Okay, so what I'm going to do is, so my recipient is Lakshita, so I'll type some message. So remember I said we can use public key encryption to sign the messages as well. So let's sign the message here to make to validate that this I have it is me that have encrypted this message. Okay, so we got the encrypted message. So if you look at here, so there are some headers, and then this is the encrypted content. So I can now copy this and share this with the other person in any non-secure channel, email or whatever. Even though these days they are also secure, but we cannot always be sure of that. So we have created the encrypted cipher. So I have now moved to the next account. So now I have received the encrypted message. So I want to decrypt that. So to decrypt, what I need is my private key, which is stored in the keybase server for this. And so to actually access the private key of my private key, this keybase provides us to provide another passphrase, so to unlock the actual private key. Okay, now if you can see, I got the message, and I also got the verification that this message was in fact signed by Amila Tracy, which was my personal account. Then we can also forget if we are not interested in like actually encrypting, but all we need to do is to authenticate that it's me that sent the message. So we can just use sign as well. So now what I'm going to do is this Amil Lakshita person will send a message. The message will not be encrypted, but it will be signed with my private key. So if someone else or the actual recipient has the public key of mine, they can verify that this particular message has actually been signed by myself because of how the encryption, how these keys are, two keys, public key and private key, are created. So let me sign this. So now if you look at here, the actual text. Oops, mouse got stuck. Okay, sorry guys, let me quickly check the battery. Okay, I might need to use the touchpad. Okay, so if you look at here, the actual message is in plain text, but we have come up with the text or message that is being signed. So I'll copy this Now I will go back to the other user's account. So he can use this verify. Okay, so it verified that this was in fact signed by Amil Lakshita. It also gave the text as well. Right. As I said previously, so this is an online website. So if we are really worried about our secrecy, we should not be relying on something like this, because someone can inject some JavaScript and actually grab these texts that we have inputted. So the whole point of encryption goes away. So so the next application that I want to show is GPG, stands for GNU PG. So this is a free and implementation of open PGP standard. So PGP stands for pretty good privacy. So it is a widely used encryption standard, and that has a defined RFC specification as well. So this also, so GPG also allows you to encrypt and sign your communications, and also provides ways of key management as well. Let me minimize this. So okay, you guys can see the terminal fine, right? I assume so. First, let me show you that we can list the keys that I have stored already. Okay, so if you look at here, I have two keys for the two accounts that I used for the keybase demonstration as well. So if you look at here, this shows as this is my personal account, and it shows some numbers as well. So this is the fingerprint, which is used to verify the actual public key that has been sent. So the issue here is, during the public the exchange of the public key, so if you have personally met and acquired the public key, we can be sure that it is authentic. But if we are getting the public key through some other online channel, maybe email, so there might we cannot guarantee that it has not been tampered with. So they then read the message and again encrypt it with the actual recipient's public key and send into the actual recipient. So the actual sender and the recipient would never know that someone else is also eavesdropping on your messages. So so let me quickly show you the So this, no, not this one. So this is my personal account. So let me. So if you look at here, this is the fingerprint of the public key. So this is not the whole public key, but this is a portion of the public key, not a straightaway version as well. So this has been created based on some algorithms inputting the public key. So if we can compare this fingerprint with the fingerprint that I have in my terminal, we can guarantee that this public key has not been tampered with, or that this public key is authentic. So if we can look at here, we can visually confirm that it is the same. So at the moment, I have not told PGP that I have actually compared the fingerprints and confirmed that this public key is authentic. So without doing that, let's try to encrypt some message to this user. So we can, let me first create a message. Okay, I have a message. Okay, so this is my message. Its content is just a text. So now we'll try to encrypt this and send this to the this Amilun 03 AC person. So the command would be gpg yes, encrypt, and we would also sign the message as well. So this armor option program to take an escape, so R is the option to set the recipient. So this is my recipient, and now I say the. So now if you look at here, so it wants me that it is not certain that the keys belong to the person named in the user ID. If you really know what you're doing, you can go ahead and do the encryption. So let's say no, and because now that I have visually compared the fingerprints and made sure that the person is the public key is authentic, I can actually let the program know that this is actually fine. So I can say can you guys hear me fine now? Okay, I assume so. Is it fine? Can you guys hear me fine?
Yes, sir. We can hear you, Amila,
Yeah.
but sometimes there are some connectivity issues.
Okay. Okay. So now I'm going to tell the program that I have I have verified the public key. So I need to use my passphrase for this. Okay, now let's try to encrypt the message again. Okay, not sure, so I might have missed some commands. So anyway, we'll proceed. So at this point, we'll say yes. So we are going to encrypt the message. So this would create another text file. Open the other screen. Bring it here. So this is the encrypted message. So now if I copy this and go to the actual recipient's PBX account, we'll check if that works. This one. Okay, so I have copied the encrypted text. So I'll go to decrypt. Yes, and we can actually get the initial message as well as make sure that it was actually sent by the correct sender. Yeah, so this is something that is used by a lot of people that needs to communicate securely. All right, so let's go back to the presentation. Okay, so we looked at one way of validating the authenticity of the public key in applications that we use day to day. So SSL and TLS. So even though like we have heard this like a million times, so actually, so there some people might not know that this means the same thing. So previously, like in 1990s, this Netscape company actually developed the SSL protocol. But later on, when the Internet Engineering Task Force took over the implementation of that, they actually renamed it to TLS to intentionally like indicate that they have moved away from the Netscape company. So basically, both these mean the same thing. So now HTTPS versus TLS. So HTTP is actually employs transport layer security to provide secure communications over HTTP. So if you look at the two small images here, so gvo.com, if you go to the browser and visit that page, it would show a log saying that browser has identified this as a secure site, and if the site does not support HTTPS, it would indicate it as not secure. So whatever the home data or content that you enter would go in plain text over the internet. All right. So when it comes to HTTPS, we also need to talk about the SSL certificate. So an SSL certificate is a data file hosted in the website's origin server. So these are issued by CES or certificate authorities, and if the particular certificate is not validated or issued by a trusted certificate authority, the browsers would not consider the server as a secure server, and would sometimes indicate it as not secure as well. And so the browsers and these other clients come with a set of certificate authorities they trust, and certificate authorities also have a hierarchy. So there are root certificate authorities and then some intermediary ones. So the actual websites that we create or that we visit, they would be validated by an intermediary one, but there's a we need some root authority because otherwise it would be a chain and there's no way of actually finishing the validation. Did someone ask a question? Okay, fine. So yes, as I mentioned previously, so what we try to achieve with the SSL certificate is to verify the server's identity, and also it provides the public key as well. So if you look at the certificate, it would like mention the things like the domain name that the certificate was issued for, and who issued the certificate, and the subdomains that are associated with it, and expiry dates, issued dates, and some other information as well. So let me try to show this. So using any of the browsers, we can see the certificate information that we have visited. So it shows the algorithms that are used and issuer and validity. So there's quite a lot of information which are used by the browser to do the actual secure communication with the server. So basically, as in the previous example, it manually verifying the fingerprint. So this provides a mechanism to prevent man-in-the-middle attacks. So and other attacks that kind of trying to impersonate the website, so users will not be fooled. So there are several types of certificates. So a single domain SSL certificates and wildcard SSL certificates. I think we in Geo we usually work with the wildcard certificates because most of the applications that we use as a public website as well as an APIs and other several APIs. So for example, Red Engine has few subdomains, and another type is a multi-domain SSL certificates. So there could be certificates that actually lists multiple domains that are not like related to each other. So these are provided by these hosting providers as a cost-cutting solution. So if you are not ready to pay a lot of money, you can go with the MDC.
Amila, I haven't seen these multi-domain certificates before. Can we use multi-domain certificates in order to get two domains under the same parent domain instead of going for the wildcard certificate? Or is that strictly prohibited? Is there a requirement saying that two domains has to be disconnected from each other?
I'm not too sure about that, Ravin.
Okay.
I will check and let you know.
Okay. So did you find a place? I mean, it's like we normally use GoDaddy and even Azure. stuff.
Yeah.
Do you know whether they offer this multi-domain thing?
Uh,
Probably it's more of a question for Hetu.
so I was looking at this Cloudflare
Uh-huh.
provider. So it lists, it provides free certificates, but they are multi-domain. So we don't have to
Okay.
pay for the certificate, but it would be a multi-domain.
Okay.
So
Good
the
to
like,
know.
yeah. So the it wouldn't, like, from a browser's or like a techie user's perspective, it wouldn't be as trustful as a single domain certificate or a wildcard. But if you are not ready to pay a lot of money, you can go with that.
Okay. Okay.
So then there are a couple of validation levels as well. So a domain, so when a certificate authority issues a certificate to our website that we are requesting SSL certificate, so there are multiple levels of validation. So the most like cheapest and the easiest validation level is the domain validation SSL certificates. So to get that, the organization was, we have to only prove that we control the domain. So maybe Ravin or Chandalo, other people who have configured this in as well. If you remember, so what we usually do is we add the DNS record or CCNAME record, and so the issuer automatically gets to know that we control the domain. So that is automated, and that is the fastest and the easiest way. Then there are organizational level validation. So this is so the organization requesting the certificate, and so there will be some manual investigation, and this will, so if you have one of these certificates, the certificate will also contain the organization's name. So I will try to show that later. And then the next thing is the extended validation. So this is the most costly one, as well as it would take a lot of time as well. So this includes a full background check of the organization requesting the certificate, as well as they will check the business is registered in the provided address, and many other background checks. But this would provide the highest trustworthiness. So this is important for like organizations like banks, for example. So previously, I actually have, why I noticed this was, I have seen in the Pizza Hut delivery online site, they also had something like this. I think it was like Gamma Pizza crafts or something. So yesterday when I was checking, it didn't have this. So I had to look at a bank one to get this screenshot. So even if you now if you go from Chrome or Firefox, this doesn't show up, but they will show it in the, so the screenshot I took was from the Edge browser. So this would show it here as issued to this company. But if we go to a normal, I don't know, let's say this, it doesn't show the organization name. So these are like just, so all three of these like validation levels provide the same same degree of in like security when it comes to the actual TLS encryption, but the difference is how this CA has authenticated the organization and how trustworthy the certificate is. All right, so now we'll look at what happens when we connect to a HTTPS site. So normally the browser will do a cache lookup and then try to find the IP of the server by using a DNS lookup, and then start a TCP connection. So as the next process, it would do a TLS handshake. So this is the part that we are interested in. So what happens during TLS handshake is so the goal is to first the browser will specify which version they are going to use, and so depending on the browser types and the server types, there are a lot of cipher sources that are available. So that is supported by both the client and the server, and then the client will also do the authentication of the identity using the SSL certificate, and it would also get the public key. then it would do some cryptographic calculations and generate the session keys, which should be then used to do the actual communication. So at this point, once the session keys are generated, the encryption is done through the actual symmetric encryption using the session keys that were generated. So the reason is, as I mentioned previously, for real life, like real payload communications, using asymmetric encryption is expensive, both in terms of time as well as the payload increase. So these systems are called hybrid crypto systems because they employ both the crypto systems, as in both asymmetric and symmetric. So this diagram I took from the Cloudflare website. So the blue part is the TCP connection establishment. So we are interested in the yellow part. So if you look at that diagram, so there are basically two round trips that have been happened between the client and the server. So the initial client hello, it actually sends the TLS version the client supports, as well as the cipher suits the client supports, and also a kind of a random set of bytes known as the client random. So once this message is received by the server, so the server would also send another message which is called server hello. With that, it would also include the SSL certificate, and the server, based on the cipher suits that the client sent it, the server will choose a cipher suit that it would like to use, and then server will also generate another random set of bytes that is called server random. So once this message is again received by the client, so now client will do the validation of the certificate, and it would also acquire the public key, and client will at this point generate another set of bytes that is called the pre-master secret. So now we have three set of random byte strings: the client random, the server random, and the pre-master. So the first two strings were communicated like openly. So if someone was eavesdropping, they can actually see them. But this the new pre-master secret that the client now generated, he would encrypt that using the server's public key, and then send it to the server. And at the same time, the client will do some calculations using these three random byte strings, and calculate the set of session keys that they would use. So that is why at this point it is saying that change cyberspace. That means at this point the client moved from the asymmetric key encryption to symmetric key encryption. So once this second message is received by the server, so it would decrypt that pre-master secret key using its private key, and also do the same calculation as the client. And because of how the mathematical formulas work, he would also arrive at the same set of session keys that the client also says that it changed the ciphertext, meaning that it also moved from the asymmetric key encryption to symmetric key encryption. So now at this point, the session keys are generated, and from now on they can continue the actual payload communication using symmetric encryption. So these steps and the different algorithms used, so they depend on they depend on the browser and the server. So this would be kind of a simplified set of steps. All right, so we talked about some session keys. So before that, what is a session? So any like conversation between two parties that is spanning a set period of time, or even till they are communicating. So for example, in WhatsApp terms, a session is a full thread of communication between two parties. It doesn't have a specific set period of time, but again, these sessions, WhatsApp sessions, can get reset based on some other external factors. So we'll look at that later. And also, so yeah, again, depending on the implementation, so the definitions, the definition of a session can change, but that's the general idea. So for the TLS encryption, so once a session expires, the parties will have to do the key exchange again and generate a new set of session keys to make sure the secrecy of the communication. So there are actually, so for TLS handshake, there are actually 4 kinds of session keys. The client write key, the server write key, the client write MAC key. MAC stands for message authentication. I cannot remember now. So and the server MAC key. So I actually didn't know about these things. So I hope some of you will also might be seeing this for the first time. So the client write key, as it stands out, is used by the client to encrypt the messages that it sends to the server. So because this is symmetric encryption, the server also has the same key, and it can use it to decrypt the actual message, and the server write key is the same thing, vice versa. And the client write MAC key and the server write MAC key is actually used to sign the messages, so the other party can validate that the actual message. So it provides authenticity. All right. So again, coming back to TLS, so these steps and algorithms that we discussed, so they differ based on client and the server support, and the real world implementations, they employ like a lot of other mechanisms to reduce the time taken, for example, to reduce the number of round trips, and also the computations. So for example, the new TLS 1.3, which was introduced in like 2018, so it adds functionality to do the handshake with a single round trip. So they try to sometimes they try to use the same, like reuse the session keys, and there are some other like complicated processes. So we don't need to really worry about them. So just having general idea is enough. All right. So now we'll quick. Oh, so we have passed an hour time. So let me quickly go through this. End-to-end encryption. So again, so basic concept employed is the public key encryption, but the real world implementations are much more complicated. So I was just having a look at this white paper WhatsApp has produced, like depicting the process it uses. So if you look at here, so there are some public keys, several public keys that are generated during the install time, and then they use several session keys. So there are a set of keys that are used to generate other keys, and then to initiate a setup. So using these initial public keys, they derive a lot of session keys, and then master keys. So there's a big complex set of processes being done. So it's not simple as just two clients having two public keys and uh, just communicating. So this also provides another like variable functionality, which is called forward secrecy. So so because of using different session keys for each of the message, so even if one session key is compromised, so there's no way an attacker could decrypt the previous messages that were sent, or the future messages that there's going to be communicated. So so this is like, if you want, I have added the link, so you can have a read and like go through it to know how like complicated these things are. But as text, I think just having a general idea is enough. And also again, like we used the fingerprint in my local PGP demo, or the SSL certificate to validate the site server's public key. So we can also, WhatsApp also provides a way to for us to make sure that the person we are chatting is the actual person. And so what could happen is, so when the public keys are being communicated, again another person can act as a man in the middle. Attack can uh, fake his public key, so that we would be sending messages to them. So we can overcome this by again comparing these fingerprints. So if you go to the contact and go to the encryption option, you can see the security code, and you can manually compare if you have the other person near you. You can even use the QR code to scan and make sure that the public key has not been tampered with, and your communication is actually secure. Or you can use this set of numbers to visually compare as well. So this is again, as I said previously, this is not the actual session key, but it is, this fingerprint is derived from it, so that even though this is visible, your security is not compromised. All right. Yeah. So my goal for the talk was to like shed some light on what goes behind the scenes, and on things like that we take granted, and also like as tech people, be mindful when we share things like passwords, and especially on live system connection strings. So I know some people, and even I think even me at times have saved these things in our sticky notes and like desktop, or just send them through other chat applications. But I think we need to be more mindful with these things. Yep. Any questions? All right. Thank you guys for listening in.